Alright, so now what we are going to do is we are going to learn how to solve homogeneous linear system of differential equations. But I think you have already seen this chapter already have an analog or a connection with chapter 4, right? Now let me go back to chapter 4 for a quick second. So let's say you have a differential equation, second order differential equation just like this. How would you solve it? This is a homogeneous one. Well, what you did is, if you can remember, we assume the solution to be e to the mx, where m is a constant, okay? And then we substitute this into the differential equation, and what do we call what we get? An auxiliary equation, right? Now, that is exactly, we take a similar approach in this chapter also. But then we have to reinvent why we specifically choose e to the mx as the solution. Can you remember it? The reason that we choose e to the mx, as if you look at the equation, this equation is a combination of y and its derivative, first derivative, and its second derivative. Now what equation says is when you add these three up, you multiply them by constant, but you add these things up and eventually you should get 0, right? So what that means is y prime and y double prime, they look alike, right? So if you think about y and y prime here, it is m e to the mx. So it's e to the mx, but it's multiplied by a constant m e to the mx. So there's no much difference between y and y prime, right? So with this can happen only with several type of functions, right? Like for example, e to the mx, okay? All right, so that is why we choose y is equal to e to the mx as our solution. Now let's go on to our new chapter then. So we have system of equations when it is homogeneous, x prime is equal to a to the x. Now what we are going to do is we are going to assume, just like e to the mx, here in this case we are going to assume our solution look like x is equal to k is a vector, capital K, e to the lambda t. Now you might think, well, isn't this capital K is the eigenvector and lambda is the eigenvalue? You are right, but we don't know yet, okay? Let's see whether they are the same thing or not. It's just we are using lambda and k as an English letter here, okay? English and Greek letters. Okay, let's see what happens. Now we're going to do is we are going to substitute this into the differential equation, the system. Now to do that we have to find x prime, right? So let's differentiate x with respect to t. So when you differentiate with respect to t, lambda counts out. So k lambda e to the lambda t. Alright, so we have x prime here. Now let's substitute. K lambda e to the lambda t is x prime is equal to a times x is k e to the lambda t. Okay, now we can do a little bit of algebraic trick. Let's switch the sides, meaning let's take this term to the right and switch the sides. So a capital K e to the lambda t minus k lambda e to the lambda t. Okay, so this is equal to 0 because you took a complete one side to the other side. Anyway, so let's see these two terms, do we have something common? Yes, right, k e to the lambda t, k e to the lambda t is common. So let's take that out. A minus lambda is left here. Now A is a matrix, so what you're going to have here is identity, okay? You cannot subtract a matrix and a constant, so it's lambda times I, okay? You take out capital K e to the lambda t equal to 0. Now we get a matrix equation. We are almost done. Now can e to the lambda t ever become 0? No, right? Exponential function never becomes 0. So we can divide by e to the lambda t both sides because you are not dividing by 0. So what you get is a minus lambda I times capital K is 0. When you divide by e to the lambda t, 0 over e to the lambda t is 0. So what is this equation? This equation means lambda is eigenvalue, k is an eigenvector. So what does that mean? Your solution x is made out of eigenvector and eigenvalue. See, if you know eigenvector and the corresponding eigenvalue, you can write the solution. So that is exactly why we learn how to find eigenvectors and eigenvalues. Alright. Alright. Now then the other thing we want to address is that, well, if you remember section 4.3, we had three cases, right? We get the auxiliary equation and we use like quadratic formula, or we factor the polynomial, and we can get three type of roots. What are the roots? Distinct real roots, repeated roots, and complex roots. Now, can you have the same for eigenvalues? Definitely yes. So there are three cases. One case is you can get distinct real eigenvalues. So let's say you have a 2 by 2 matrix. You can have two different eigenvalues, real numbers. A 3 by 3 matrix, you should have three different real eigenvalues. So that's a one case. Or your system can have repeated eigenvalues. So let me quickly show. For this matrix, I highly suggest you to do it by yourself. Here, if you find the eigenvalues, we get the eigenvalue. We get like the characteristic polynomial as lambda minus 2 square is equal to 0. So the eigenvalue is 2, but it's squared. That means 2 appears twice. So this eigenvalue is repeated twice. So that is a repeated eigenvalue. Then the way we solve the differential equation is totally different. Or the way that we write the equation solution is totally different. Okay. And then we can have complex eigenvalues. So for example, characteristic polynomial here is lambda square plus 27 is equal to 0. So the eigenvalue is plus or minus 3i. Okay. If you factor this, so use the quadratic formula. So the same thing can happen to us when you're finding eigenvalues. So based on what type of eigenvalue you get, the way we write the solution is different. So we are going to address these three cases in 3 videos. Here, let's gonna address distinct real eigenvalues. Really, 3 separate lessons, okay? So distinct real eigenvalues is the easiest case. So let's say, for example, you have a 2 by 2 matrix. Let's assume, okay? Let's learn it from an example. So here, you have this differential equation. You write the matrix A, you find the eigenvalues. Let's say the eigenvalues are 3 and negative 2. Because you have a 2 by 2 system, you should have 2 eigenvalues. They are distinct clearly, right? They are not the same thing. Now, let's say the eigenvectors are negative 4, 1. 1, 1, the corresponding eigenvector. So this is an eigenpair, eigenvalue and eigenvector. Now this falls under the case 1, where you have distinct eigenvalues. Now the way you write the solution, the final solution, general solution is very simple. But let's write down the fundamental set of solutions. So the x1 is k times the eigenvector times e to the lambda t. Here lambda is 3t. So that's the x1. The second solution is second eigenvector times its eigenvalue, relevant eigenvalue, negative 2 e to the lambda t. So these are the two solutions in the fundamental set of solutions. Okay. So that is how you write. But don't mix up the eigenvectors and the eigenvalues. So for example, for negative 4, 1, you cannot use negative 2 here. Okay. They have to match. They have to be the corresponding eigenvalue and eigenvector. Now the way you write the final solution is, linear combination of C1 x1 negative 4 1 e to the 3t plus a constant times 1 1 e to the negative 2t. So this is the general solution. It is same as auxiliary equation solution. Remember, when you have distinct roots, the solution will be like y is equal to C1 e to the 3t plus C2 e to the negative 2t, right? But instead of, but here, since we are dealing with vectors, we have our eigenvectors here, right? The corresponding eigenvectors. So that's the difference between systems and the single differential equation. One difference, if you want to compare and understand it correctly. Okay. All right. So that is how we deal with distinct real eigenvalues. It's simple, right? But all the game is to find eigenvalues and eigenvectors. So solving a differential equation is same question as find eigenvalues, find eigenvectors. Depending on what type of eigenvalues you get, you write the solution in the appropriate way. Okay. All right. So let me finish the video on the note that the question that I asked in the beginning. Now, why do we assume our solution to be like eigenvector times e to the eigenvalue times t? Now, why did we choose e to the mx in section 4.3? Because when you take the derivative looks like the original function. Here the same thing. Remember, when you take x prime, k lambda e to the lambda t is same thing, but it's just a different from a constant lambda. Right, lambda is a constant. So again the same idea, this is similar thing like as e to the mx. Okay, so that is how we deal with the homogeneous linear systems. Remember, we have three cases depending on the type of eigenvalues you get. But if you get distinct eigenvalues, the way we write the solution is just it's a linear combination of your fundamental set of solutions. So I highly recommend you to go through every my video solving me examples in the note, because you have to learn how to do this for 3x3 systems and both 2x2 systems, solving a full problem. Okay, all right then, thank you very much.